Okay, hi. Last topic of Unit 6. Yes. Quantifying heat change in reactions, or enthalpy of reaction. So, in chemical changes, we'll use enthalpy as our form of heat that we use to calculate heat of reaction because our chemical bonds are broken and formed. And we said that anytime we're disrupting forces of attraction, whether it be chemical bonds or whether it be intermolecular forces, we have to deal with enthalpy. So what we need to think about is how do we quantify this? You looked at this a little bit in 6.5 when you took those chemicals, you broke them apart in the gizmo, you kind of put them back together, and then you looked at how this, or what it would do inside of a calorimeter. Would it increase the surrounding temperature? Would it decrease the surrounding temperature? So what we want to be able to do is use our tables of values to be able to do this without having to plug these things into a gizmo or a simulation. So I'm going to give you an equation. To calculate the change in enthalpy, really what we have to think about is how much energy do we put in versus how much energy do we get out. So we want to first start by thinking about the amount of heat that is absorbed by reactants. This is the amount of energy that's used to break bonds. So I'm going to write that above 2. So heat, break, bonds. Okay. Then we're going to take the amount of heat that we're going to get out when we put our things back together. So this is going to be heat released by products. And this happens when we form bonds. So our final equation that we're going to put together in mathy language says the delta H for a reaction, or the change in heat for a reaction, is equal to the total sum, that Greek letter represents sum, so the total sum of the energy of our reactants bonds minus the total sum of the energy of our product bonds. So this is how much energy do we put in, subtract out how much energy do we get out. So every bond that holds atoms together, single, double, and triple, will have a different amount of potential energy that's associated with it. So the potential energy is stored energy, chemical stored energy that holds those atoms together. So if you take a look at the table right here, this is an example of a table that you could be given on a test or something like that. You have to be given the information. You won't solve for the bond enthalpies in this class. You're just going to be given the tables and then asked to use them. So what we can do is, based off of Lewis structures and based off of balanced chemical equations, we can use our table of values to help us figure out the total delta H of a reaction, the total change in enthalpy. It's based off of the types of bonds that you have present and the number of bonds you have present. So we're going to take a look at example 1 together. C2H6 plus Cl2. What I want to first start by doing is think about how much energy is going to be required to break those bonds in my reactants. So if I take a look at my Lewis structures that I've given you here, I notice that I have CH bonds as one of my types of bonds. I have CC single bonds as one of my types of bonds, and then I have a CL-Cl bond as another type of bond. So these are my 3 types of bonds that I have to break. I've got CH, I've got C single, and CL-Cl. Okay, here's my recommendation. The first thing I think you should do is count up the number of bonds that you have present in the structure. So for C2H6, I have 6 CH bonds in that structure. I highlighted those in blue. So this is my number of bonds that I would have to break. Okay. Then the next thing I'm going to do is I'm going to look at my balanced chemical equation. The mole ratios in the front, the coefficients, they also represent those number of molecules, right? So I only have 1 C2H6 molecule in this structure, so I'm going to multiply it by 1 to remind myself that's the mole ratio. The last thing I'm going to do is I'm going to figure out how much energy is required to break those CH bonds. And I have to get that from my table. So from my table, I see that the energy to break a CH bond is 413 kilojoules per mole. So I'm going to write that right into here. Okay, next is my CC bond. So I have one CC bond in the structure. I have 1 mole of that molecule in the equation. And to break a CC single bond, if I look at my table, I did that one in pink, 347 kilojoules per mole. Last one is ClCl. So I have 1 ClCl bond. I have 1 mole of it in the chemical equation. And to break a ClCl single bond, it takes 239 kilojoules of energy. So when I sum these all together, this is going to be the total energy that I have to put in to my system. I'm going to do this really quick on my calculator for us. So 3064 kilojoules is the amount of energy that has to be absorbed. Now, if I think about the energy that's going to be released, this is going to come from my product bonds. So if I look over at my product bonds, let's figure out how many types we've got. So I've got CH bonds still. I've got a C single bond still, but now I have 2 new bonds. I have a CCl single bond, and I have a HCl single bond. Okay, so let's start with the ones we already did. Well, I have CH bonds again, but this time in my structure, I only have 5 of them. I still am making 1 mole of this molecule, but it'll take the same amount of energy to form those bonds. Next is CC. So I have 1 bond times 1 mole times the same amount of energy to form that bond. Now I've got 2 new ones. Okay, so I have a CCl single bond. I make 1 of those, that's highlighted in orange. I have 1 mole of it, and the energy to form a CCl single bond is 339 kilojoules. And last but not least, HCl. So my HCl single bond, I have 1 of them. I have 1 mole of it in the structure, in the chemical equation, and the energy to make an HCl is 432. 432. Okay, so I'm going to sum these for us really quick. But when I sum these, what I get is the total amount of energy that's going to be released when my product bonds form. 3,183 kilojoules. Now I look for the net change. I'm going to take the energy that's in, or the energy absorbed, and then I'm going to subtract out the energy that I get out when my product bonds form. Clearly, you should be able to see what the sign of this is going to be just based off of the numbers that are bigger. The second number, the energy out, is bigger than the first number, so that tells us we should be getting a negative value, and specifically we will get negative 119 kilojoules. So this tells us, because this is negative, this is an exothermic reaction. So when we solve for this delta H reaction, this can now go into our thermochemical equation. I could write plus 119 kilojoules at the end of this to show this is an exothermic reaction, and specifically that much energy will be released when the reaction occurs. So if I want to sketch my reaction diagram, my potential energy diagram, all I have to do is just a rough sketch here. This is my reaction progress, what happens to the reaction over time. Potential energy goes on my y-axis. And because this is an exothermic reaction, I know that my reactants are going to start higher in energy than my products. And then all I have to do is just put in my little labels. Here's my activation energy. I don't actually know what the value is, so I'm just going to draw a general curve right there, and this is my delta H. Okay, you're going to do one more practice problem now. You are going to do the one right down at the bottom, and then check your answer at the end. Bye!